Thank you for having me. So I did want to say before I got started that some of what I'll be presenting today is from joint work with Arc Kocurek from Cornell. I actually realized when I practiced the talk today that I probably won't get to that part, but if I do, I will indicate it. All right. Wait a minute. How do I go to the next slide? There we go. Okay. So what my project across a few papers actually is to axiomatize a two-dimensional Deontic logic that I defended on natural language grounds in my dissertation, which validates the form of free choice permission and witnesses the non-entailment known as Ross's puzzle. So these free choice permission and Ross's puzzle are sort of classic puzzles from the Deontic logic literature. They might be familiar to everyone here. You see free choice permission in one. So if I say something like, in English, you may have an apple or a pear, that seems to carry a felt entailment to the wide scope conjunction. You may have an apple and you may have the pear, of course, not both at once or not necessarily both at once, but that each is permissible. And that's sort of surprising if you're thinking of this as a semantic entailment and you have, a diamond semantics for may and a Boolean semantics for or, then this wouldn't be valid, obviously. But it seems valid. And then Ross's puzzle in 2 is the failure of an entailment, which should be classically valid. So you reason as follows, I ought to post the letter, therefore I ought to post the letter or burn it. That sounds like a non sequitur. So what it looks like in a sense is that or introduction is blocked in the scope of ought, which would be unexpected if ought were a box and or was the Boolean or. So when I got interested in the logic of this, a big picture thing I realized that I would want to do is to reject necessitation for ought and then to explore a proof system that, that would allow that. And there's kind of a two-dimensional precedent for this in the literature. So of course, this equivalence, the diamond distributes over the V, and the box P entails box P VQ, those are valid in any normal modal logic, including standard Deontic logic, which is normal. So the negations of 1 and 2 are sort of embedded in proof systems. If you want to reject them without, I don't know, killing everything, then you need to sort of excavate the foundations of the propositional tautologies. So that's sort of what I'm going to be doing in the big picture. The resulting system, one way of putting it, is it pursues the intuitions that classical propositional tautologies involving disjunction, like law of the excluded middle, are truths of meaning rather than propositional necessities. So typically you take the tautologies, of non-modal fragment, and then you just necessitate all of them. But I'll say, well, these are a priori truths, they're not necessary. So that's the status that, for example, the law of the excluded middle will wind up having. So of course, that's sort of a departure, to say the least, from commitments that the propositional fragment of a modal proof system is standardly taken to embody. Though I do think that in sort of the heyday of some of the excitement about Kaplan's two-dimensionalism, for example, there were precedents for this that were sort of explored conceptually, although not in the way that I do it. For example, this paper by Zalta in 1988. So first, I'm going to sketch what I'll just call the basic 2D language. My exposition on that leans on the two-dimensionalism of Kripke and Chalmers, but maybe in particular on Stalnaker's assertion, where he has a pretty different discussion of the dagger operator and diagonalization, which is an important concept for Stalnaker for lots of applications, actually. Then I'm going to introduce a two-dimensional disjunction that I think comes from, although it's debatable, comes from Grotendijk and Stockhoff's work in the 80s on WH elements, and then this little paper by Lewis in 1982 on weather ascriptions. But I see that as a precursor to the kind of thing I'm going to do for the or that appears in sentences 1 and 2. That disjunction is expressible in the basic 2D language. So that's how I will sketch a logic that contains every classical propositional tautology, but doesn't validate the inference in 2. Propositional tautologies involving natural language or the rule of or introduction from P, infer P or Q, that's going to be an a priori valid inference. And things like the law of the excluded middle are going to be a priori truths which can't be necessitated. So they'll sort of have the status of logical truths in Kaplan's logic of demonstratives, for example. That open space, so this is all just to block the entailment in 2, right? That open space for the holding of the strong non-classical entailment pattern 1 in free choice. It doesn't explain it. I would have to do extra things for that, which I do, but I probably won't get there. There are some, I think, when I started to explore this literature, it turned out that even doing that with a basic 2D language was kind of a big project. So I think that there is a self-contained goal in the first part, which is to gain a greater understanding of the relationship between crypty models and the well-known matrix models that Stalnaker uses in assertion and in our knowledge of the internal world, and in other places, and the relationship between sentences and propositional concepts in natural language. And if we get to it, which I probably won't, I'll transition to a particular application relevant to the entailment in 1, the strong entailment of free choice permission, which is for deontic modal operators and deontic logic, because at the beginning I won't even have deontic. There won't be anything about the operators that makes them specifically deontic. All right, so I do assume that a lot of people in this audience are, well, I know for a fact that a lot of people in this audience are familiar with two-dimensionalism, but I'll crash through it in one way or another. So, of course, the basic difference in the semantics is that in two-dimensional semantics, our formulas are satisfied relative to, instead of a single world and a model, a pair of worlds taken from a model, right? Write those as y, x. Typically you think of the sort of y parameter world, the one that's written first over here, as the world as actual. And think of the second world, the X world, as the world of evaluation. So for example, we'll have a box, which is just the simplest sort of global quantifier over the world of evaluation. So the basic idea here is things like indexicals, which are set by context. Those are rigid in the scope of modal operators like the box. But other than that, our relation will be universal. I'll just quantify universally and say yx satisfies box phi, if for all x prime, yx prime satisfies phi. And so that global entry, for example, that you find in Crossland Humberstone. Here are our 2 other operators. So this is actually, right? So actually takes you from a point yx and looks at the truth value of phi at the corresponding yy point. So, the value of y kind of swings out to the x there. And then the dagger operator basically does the opposite, right? It takes yx and it asks you to look at the point xx where x kind of swings left. And so these are both diagonal points where you're looking for the truth value of the projacent phi, but you're looking at different ones. Here you're looking at the y parameter point, here you're looking at the x. So visually it looks a bit like this. You're starting with a set of worlds, you're making a 2D array, right? The diagonal is here, here, and here, sort of at 1, 1, 2, 2, and 3, 3. And then I'm using red arrows to represent the actually operator. So that'll take anything to the diagonal point of its row. And I'm using blue arrows to represent the dagger operator. So that will take any world to its column diagonal point. Where do we go from here? Well, in two-dimensional semantics, we're interested in modeling sentences like 3a, everything is as it actually is. That seems to have some status as true in some especially robust sense. I maybe know it's true without looking at how the world actually is. I know that everything is as it actually is. But it would be funny to conclude, even though this has something like a tautological status, that I can necessitate it and conclude that necessarily everything is as it actually is, because that would collapse modal space. I don't think it's necessary that everything is the way it actually is. Necessitation looks a bit funny for examples like this. To sort of model that, think about, I'm going to add rather a kind of zero-ary operator to the language or a special constant, which I'll call bow tie. So say that bow tie is the maximally fragile diagonal truth. So yx satisfies bow tie just in case y equals x. It's true everywhere along the diagonal and nowhere else. So the goal of bow tie is to sort of go proxy for a sentence like everything is as it actually is. So we can think of, maybe we think, well, in some sense, like the sense Kaplan was trying to get at in demonstratives, bow tie is a logical truth. I don't have to look at the world to see that bow tie is true. But suppose necessitation holds, right? If phi is a logical truth, then so is box phi. Well, then you would get that box bow tie is a logical truth, which seems to be no good. Obviously, there are more examples. Here are more, right? Sort of the Wittgenstein sentence, the standard meter is 1 meter long, back when there was a standard meter. That seems true, however long it is, but it seems false that the standard meter could not have been longer than a meter. I know for Cartesian reasons that I exist, I wouldn't want to conclude that I'm a necessary being. You know, the A sentences seem good, the necessitations of them don't seem so good. So the difference between metaphysical necessity and a priority, maybe we want to say these sentences are a priori, can be regimented in the 2D framework as a difference between some sentence phi is holding everywhere along the x-axis, that's kind of our metaphysical necessity dimension, and holding everywhere along the diagonal. So we can introduce this operator, A for a priori, and we'll say yx satisfies a priori phi, just in case for all z, so just quantify away from both of these points, zz satisfies phi. So maybe what we want here for sentences like 3, 4, and 5 is something like a rule of a priorization rather than a rule of necessitation, or for sentences that are approximated by bow tie. So I want to say something like, well, if I can conclude phi from nothing, if it's a tautology in that sense, then maybe it's a priori that phi, right? And we can express that in the basic 2D language because we can write a priori as box dagger. So it would be the same as saying, if I can conclude phi from nothing, then box dagger phi. There's the picture again. So that's one way of breaking down a priori. Of course, another way that's prominent in the literature is you can also break down a priori as fixedly actually, which is something that Humberstone explores. So why do it this way? When I started the project, I was surprised to learn that I hadn't seen dagger axiomatized, so that decomposition of a priori into box dagger was explored. You know, because I thought, well, you know, diagonals are important. They're important for communication. They're important for rational thought and so on. So here's just a how Stolnacher would frame diagonalization. He does it by introducing uncertainty into a situation where speakers are using context-sensitive language, like indexicals. So this is a quote from Assertion. Let me give a simple example. I said, you're a fool to O'Leary. O'Leary is a fool, so what I said was true, though O'Leary doesn't think so. Now Daniels, who's no fool and who knows it, was standing nearby and he thought I was talking to him. So both O'Leary and Daniels thought I said something false. O'Leary understood what I said, but disagrees with me about the facts. Daniels, on the other hand, agrees with me about the facts, but misunderstood what I said. Just to fill out the example, let's add that O'Leary believes falsely that Daniels is a fool. Now compare 3 possible worlds, I, J, and K. I is the actual world, basically. J is the world that O'Leary thinks we're in, and K is the world that Daniels thinks we're in. So the following 2-dimensional matrix, actually, I would paraphrase this slightly. The following 2-dimensional matrix represents the 2 ways that the truth value of my utterance is a function of the facts. So here's his picture, right? So along the 2 axes, we have I, J, and K. So, you know, these squares are sort of ordered pairs of those worlds. And then we'll just treat you're a fool as an atom, call it P, right? And then that atom takes truth values at each one of these points. So there's a bunch of different ways to look at this. One is that the world is actual, which is what we've sort of by convention put along the y-axis, is going to disambiguate the indexical u. And then you can read across the row to see the expression that this sentence, to see the proposition that this sentence expresses once the indexical is sort of resolved by which world you take to be actual. So for example, here for I, you is the person that Stalnaker in the example was actually talking to, i.e. Daniels. So it expresses the proposition that Daniels is a fool. Daniels is a fool in the actual world. Daniels is not a fool in the world according to Daniels, that's world J. And Daniels is a fool in the world of, sorry, O'Leary. O'Leary is a fool in the actual world. He's not a fool in the world according to himself, O'Leary. He's a fool in the world according to Daniels, so we get TFT. We get the same row, TFT, over here for J, and that's because O'Leary is correct, or O'Leary and Stalnaker agree on what was said on the proposition that O'Leary is a fool. Of course, they don't agree on the truth value, but they agree on the proposition expressed. Here, this is the world according to Daniels, right? So he thinks U refers to Daniels. And so if he thinks it expresses the proposition that Daniels is a fool, Daniels is not a fool in the actual world. Daniels is not a fool in the world according to him, Daniels. And he is a fool in the world according to O'Leary, so we get FTF. So that sort of matrix just like captures all the information. But one of the things that Stalnaker is highlighting is overall, Stalnaker himself thinks he said something true, right? O'Leary thinks he said something false, and for a different reason, Daniels thinks he said something false. So you sort of get the agreement and disagreement profile by looking at the diagonal. One way of sort of glossing that is that what diagonalization does is it's a way that we interpret when we disagree about what the world is like and what proposition is expressed by the sentence depends on what the world is like. We can diagonalize to get rid of that dependence. He sort of gives a meta-linguistic gloss on it. What is said in S's utterance of phi is true, where the definite description, what is said in S's utterance of phi, may be a non-rigid designator, a description that refers to different propositions in different worlds. So the solution is to sort of, when you don't know what was said because you don't know what the world is like, you have this free parameter, right, when you're trying to interpret the proposition expressed by phi. But if you diagonalize, then you would reduce the arity of that expression. So you would get a proposition that you could calculate at every world, say in your context set when you're exchanging information. So that's diagonalization. He glosses it as a kind of interpretive strategy for situations where context dependence is unresolved because of uncertainty. The O'Leary example, maybe it's worth noting that in that original example, it involves a misunderstanding, right? Daniels is just incorrect about who Stalnaker is talking about. But sometimes the failure to know which world a dialogue takes place in can be recognized by all parties without any fault, I think. For example, when you're facing the metaphysically open future, if you're making statements about chance in the open future, for example, the metaphysics don't settle which world is actual. So that would be a distinct reason to need to diagonalize because there's no fact of the matter about what proposition was expressed if you continue to anchor the proposition expressed to which history becomes actual. Okay. So just for people who remember, this is assertion in its original glory. So this is very much sort of the kinds of models that Stalnaker used for those expressions. And here's diagonalization, right? He calls this, a propositional concept E, propositional concept because there's a possibly distinct proposition along each row. And then he says, well, you would, a moment's reflection shows that what the speaker is saying is really the diagonalization of that. Because, for example, here that winds up being a contingent proposition. So visually, the dagger will take the diagonal and project it across the horizontal. So, I read assertion and I thought, well, okay, those models are helpful, but what kind of models are they? I mean, are they cookie models or whatever? So there's that. Now I wanted to mention something somewhat different, in the context I wrote completely different. But still not carrying in this framework because it'll be important, and sort of relating it to what he's doing in assertion is possible, but I think I won't try for reasons of time. Which is to say that in addition to classical consequence, it's important to Stalnaker and others that there's an informational notion of consequence at play when we model natural language, which defines validity in terms of the preservation of acceptance, not just truth. So in a static one-dimensional framework, acceptance can be modeled as global truth, truth relative to every world in the context set. So if we're thinking about the worlds that form the arrays of the axes in a two-dimensional array as things that are possible at a context, then what we would want to be tracking for an informational notion of consequence is really sort of what happens if you box all the premises and the conclusion. So say, gamma informationally, generally, so now we have sort of two axes to distinguish general versus diagonal truth and consequence, and also classical and informational. So say gamma informationally generally entails phi, whenever box gamma classically generally entails box phi. And so we can introduce a box in front of everything that goes here, but it also seems like if we're interpreting things as their diagonals, then we're diagonalizing the proposition as well, possibly before we do that. So the notion that I'm going to be interested in for validating, for example, the inference in 2 and validating the inference in 1 and blocking the inference in 2 for the Deontic puzzles is going to be this notion here of diagonal informational consequence. So it's going to be box dagger gamma entails box dagger phi in general. And that you can see that as a kind of a priori consequence. Again, the box dagger combination is equivalent to a priori. So I'll just use a special symbol for that. I'll use the little right triangle. So we have a priori consequence, which we'll notate with this. And then we have this notion in the language of an a priori sentence. Even though there's different kinds for those, it's just going to be, we could just use a bow tie as an atom for that. Okay, so with those sorts of considerations, there's sort of 3 questions to think about. First, what class of modals or frames are we interested in when we think about adding actually and the dagger to a modal language? Again, if we're adding it to a modal language, then we have a box, and we can use the box dagger to model a priority. How should we think about axiomatizing additional contingent a priori truths, if there are any, treating them compositionally, for example? And how should we think ultimately about adding a Deontic submodality of metaphysical possibility to this language? Because again, I've been sort of assuming the box is kind of this global S5 relation that would be a better fit for metaphysical possibility than for anything having to do with Deontics. Deontic accessibility is obviously not S5. Okay, sorry, I guess I have that picture everywhere. So start with frames. So I want something that looks kind of like the Stalnaker matrix. So let's say a basic matrix frame. I'm taking these definitions from Peter Fritz. Is a Kripke frame Wx and then R square X, R actually X and R dagger X, where Wx is some X by X array for some set X. Let's say non-empty. And then these are sort of what you would figure, right? The R relation, again, quantifies sort of horizontally. So any yx point is R square related to a y prime x prime point, just in case y prime equals x prime. So as long as the y parameter doesn't change. The actually operator will take you to a diagonal point, right, where y prime equals x prime, but in particular, that value will be set by y. And then the dagger will do the opposite, so it'll take you to a diagonal point where y prime equals x prime, but that particular value is set by x for your starting point. So these relations are functional, which is sort of what they look like in the picture. And this one is certainly not. So let's get a proof system. Let 2D be a proof system axiomatized by modus ponens, uniform substitution, Boolean tautologies, the K axiom and necessitation for each primitive modal operator, and the following axioms. So I don't really know in logic talks whether people tend to dwell on these sorts of axioms, but let me go ahead and do that a bit because this was a healthy amount of work for me. So the T and 5 axioms, right, just tell you that the box is an S5 relation. It doesn't tell you that it's global, right? This one, I don't know, actually 5 for the diamond. This one tells you that actuality is rigid, right? So if you look at the contrapositive, for example, it would tell you that actually P tells you that it's necessarily the case that actually P, because the box quantifies across the horizontal. So it's not going to take you from any world to a world that sees a different world as actual. G is for globality. So that just tells you that the quantification that you do with the box will include whatever world is actual on the sort of row of the matrix, if you want to think about it that way. Functionality, so actually is self-dual. The dagger is also self-dual. So these are sort of X and Y arrow. You can prove the interior biconditional from just these directions. So basically this says within the scope of the dagger operator actually is redundant, and within the scope of the actually operator, the dagger is redundant because you're already at a diagonal point. So these ones are standard and don't involve the dagger, these ones do. And then the way to look at these guys, the reason why I wrote 4A and 5A is just because that combination is a priori, right? So this says if it's a priori that P, it's a priori that it's a priori that P. Call this, it's sort of the dual of a priori, maybe conceivability, something like that. So it's conceivable, if it's conceivable that P, then it's a priori that it's conceivable that P. So 4 and 5 axioms for a priori. So that axiomatization is sound and complete for M, so that's for the class of basic matrix frames. So a way of thinking about that is, did I write this? No, I didn't. All of these guys are Sahlqvist formulas. So there's a class of Kripke frames for which completeness is immediate. Of course, that's sort of the wrong class. So we need to take that class of Kripke frames and sort of squash it down and show that it's modally equivalent to these matrix frames, these sort of square things, which you make with a 2x2 array. So how did I do that? I was following pretty closely a strategy that Fritz uses in a 2014 paper. So Fritz is axiomatizing a priori, but he's not breaking it down into the box and dagger like I am. But the way that he did that is to sort of, over here, what you have is point-generated subframes of the set of frames for which completeness is immediate by Sahlqvist. And so these aren't necessarily square, right? You cannot express squareness in the relevant modal language. But we're using 2 results. One is modal satisfaction is invariant under point-generated submodel, so that's why I'm considering this class, which he calls a rest-all frame, after some work Greg did. And also that modal satisfaction is invariant under surjective homomorphisms. So once you have this, the sort of the rest-all frame, the point-generated rest-all frame, you can create, these boxes represent the sort of those S5, the cells of the S5 relation that you get with the box, the metaphysical box. So you can identify those, and then you can identify the fixed points of actually and the dagger. So those are sort of these worlds, let's say. These arrows represent the actually operator. And what you want to do is build a sort of much fatter matrix
model that captures the same information that you have here by sort of creating a bunch of duplicate worlds, but observing a surjective homomorphism where every world that's diagonal on the diagonal here, or every ordered pair that's in the diagonal here, gets mapped to one of the fixed points of one of these cells. So for example, this is sort of 1, 1, right, in the array. So that goes to world 1 because world 1 is the fixed point of this cell. And then you have all this other space to work with. And here there's only one other world in the cell. So these guys all just go to here. You'll do the same thing. This is for row 2, this is for rows 3, 4, and 5, and these will go to the distinct diagonal point over here. Okay, so what I'm doing is, what I did for this was quite similar, except that I had to add coordinating the dagger relations as well. What is there to say about how I did that? Again, I wasn't sure how much detail to go into. Here's a homomorphism that's quite similar. What I'm taking is I'm letting W be the size of the original Restall model, the cardinality. D is the number of diagonal points that you can identify in the model. So this is enormously bloated relative to the information here. And I'm just firing these things so that they land where they're supposed to go. And I've partitioned the cells, the S5 cells, according to which world they're dagger related to. So when I was doing this, again, just to sort of, because I was sort of new to this kind of project in logic when I started this, I learned some morals in doing this. One was I became obsessed with finding the smallest matrix that will capture the information in a Restall model. And then I talked to Larry Moss, who pointed out that I had absolutely no need to do that. And I could make, I see Greg nodding, I could make this guy as monstrously bloated as I wanted relative to the Restall model, as long as it would capture the same information. So there's just many, many copies, basically, of the worlds here that you find over here. So that was very liberating in the context. So there's a theorem. 2D is sound and complete for M, the class of basic matrix frames. One thing that made this quite easy to do, which is why I think Peter chose the original strategy in his paper, is that when your operators are self-dual, like you have here for the functionality of actually and the functionality of dagger, a lot of those complicated Sahlqvist formula conditions become vacuous, or they become trivial, because you have to be afraid of whether boxes go over diamonds and things like that. But if the box is the diamond, then those things all sort of collapse. So it was actually very easy to come up with Sahlqvist friendly axiomatization. It was just the obvious one. Great. Okay. But let me say a little bit more. What class are we interested in, right? So we can approach the other thing I was interested in for this project by asking sort of the following question: is the space of worlds or the space of world pairs fundamental to the model? So the reason I say that is because we generated a matrix frame by just taking some set, whatever it is, and crossing it with itself to make this array. But the set of worlds that you throw into a modal model is supposed to represent something important. It's supposed to be the space of possibilities. So an Akvist logic, for example, this is picking up on terminology from Akvist and Segerberg in the 70s, can be seen as taking the space of worlds rather than world pairs to be fundamental. Why? Because of its relationship to the language. So an Akvist logic interprets atoms of the language as functions from worlds to truth values that are constant in the y-coordinate. That is, as propositions in Stalnaker sense, right? So Stalnaker says sort of fix what row you're on and then read across the proposition. He doesn't think of a proposition as the two-dimensional array. He thinks of it just as the row that you get once you fix a world as actual. So, for example, in this framework, there's a sense in which the box in the semantic entry for the box models this all-inclusive global modality, right? It's supposed to be S5. It's supposed to be, maybe it starts out at the beginning of your life as an agent or something as maximal in some sense over the possibilities that exist. So it's supposed to be global, but the implied accessibility relation for the box is not, of course, global on the space of world pairs, right? Because it is confined to the horizontal. That's sort of the whole point of two-dimensionalism. For actually to remain rigid in the scope of the box and diamond, which is what we wanted, the box can't shift the y coordinates. So you could sort of, this is just to say that you could define a box that's hyperglobal, but that's not what we're doing. Our box is global for x and not for y. So seeing the two-dimensional entry as expressed in global modality depends on taking the space of worlds rather than the space of world pairs to be fundamental to the model in some sense that interested Akvist and Segerberg. So what Akvist did was introduce this restricted axiom. I don't really know what this is called, halo A. And it says dagger alpha is equivalent to alpha for any alpha that's in the atomics. So what that would mean is, sort of visually, if you want, I don't know, let's say gray is true and white is false, right? So you have these matrices, and the atoms, P, Q, and R, are going to have this kind of like visual barcode property. If it's true here, then it's going to be true at the relevant diagonal point, and vice versa. So, you know, this is T, 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 F, 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 like you would get in a truth table, T, T, F, F, T, T, F, F, T, F, T, F, but the point is they're all stripes. To give some preview of how OR is going to work, for me, this is actually an illustration of what you would get if you, from these atoms, if you constructed P or Q, Q or R, and P or Q or R. So the point is, of course, you will eventually get matrices that fail this uniformity property, this Akvist axiom, but you'll only get it by compounding with operators, like OR. Of course, for me, OR is not the Boolean join, so that's why something like this is possible. But you start with atoms, and then sort of anything that's going on that makes the Akvist axiom fail sort of has to be visible to the compositional semantics. So as Segerberg, you know, is at pains to emphasize, an Akvist logic, therefore, is not closed under uniform substitution, right? There's this special rule that applies only to atoms. It's closed only under substitution in the 1D fragment of the language. So, you know, for example, you could do Boolean stuff in alpha. But my OR is not Boolean. So this limitation for closure under substitution follows the spirit of, I think, several people. I mean, I found it in Williamson, for example. He says the obvious rationale for insisting on closure under uniform substitution in a propositional system is reading the non-logical sentence letters as propositional variables, as variables that range over propositions. But again, propositions are these special guys for us. Virja says something similar. And so I take it that actually this is part of kind of this literature that I learned about from Lloyd's book on just why we have uniform substitution and sort of what its status in a logic is, or how we should think about what it's supposed to mean. That typically we frame our logics as having uniform substitution. So let's be Akvisty for a while and look at the same thing. So let's say a matrix model of the kind we had before. These should have little x's. And then there's the valuation function, because it's a model and not a frame, is Akvist, just in case, for any x, y, and y prime in W. If xy is in VP, then so is x, if yx is in VP, so is y prime x, right? So I can travel up and down. It won't make a difference to truth value because it's barcode. So let's let 2D A halo be the Hilbert-style proof system consisting of modus ponens, necessitation for each modal operator, our restricted axiom, A halo, and then this axiom schema, phi, wherever phi is a theorem of 2D, so the language that we already, the thing that we already did. So theorem 2, 2D A halo is sound and complete for strict classical consequence over MA. Oh, and I'm sorry, there should be a little halo here too, right? This class. So if you want to move to the framework, and I do for the purposes of my Deontic puzzles, I do want to move to a restricted class of models, which is not just all these matrix frames, but they have this special feature of the atomics. So this is the proof system that will do that. This doesn't have uniform substitution. I believe in the formal epistemology literature for the Daisei and so on. These guys, instead of being called akvis, are called boring, and that is a technical term. Okay, so zooming out a little bit, let's return to the strategy for the Deontic puzzles that I sketched sort of in the introduction. What we seem to need for 1 and 2 is a two-dimensional semantics for disjunction where or introduction is a priori but not necessary. So why do I want that? I see I have not listed it. Basically, the reason I want it is because I want to block or introduction in the scope of ought for 2, right? But I don't want to block or introduction outside the scope of ought. I would like or introduction to be a priori valid, and I would like tautologies like P or not P to be truths of meaning. You can conclude them from nothing. You can begin proofs with them in the relevant way. But if you look inside a modal operator, then the or will display non-classical behavior. So it won't follow from the fact that you can start with P or not P that you can necessitate it and go to necessarily P or not P. Likewise, I want to be able to say from the fact, no modals now, from the fact that you posted the letter, you can conclude I posted the letter or burned it, but you can't conclude from I ought to post the letter, I ought to post the letter or burn it. So I want a two-dimensional semantics where or introduction is a priori but not necessary. Okay. So such a semantics, I think, is suggested by Grothendieck and Stockoff and Lewis's two-dimensional approach to whether P or Q attitude description. So notice, this literally does have what I think is a compositional occurrence of or in it, but this is a quite different literature. It's on attitudes like know or ask. That's not really an attitude. Wonder. So you can say things like Bob knows whether P or Q. Bob wonders whether P or Q. And notice, right, that a sentence like 6 credits Bob with knowledge of the actually true answer to the question, the disjunctive question, if you want P or Q, right? So this does not credit Bob with knowledge of the Boolean join of P and Q. It credits Bob with knowledge of something more specific, either P or Q. Which one? Depends on how the actual world is, right? So that's the intuition. So Grothendieck and Stockoff treat whether P or Q complements to attitude verbs compositionally, as does Lewis, but not in quite the same way that I will. So here's a simple way to do it, to kind of model a disjunctive question in this way. Create a little answer operator. So let that be parameterized to a particular world. And then it'll take 2 sentences, phi I, phi j, and it'll give you the singleton containing, let's say, phi I, if phi I is true at W. Now we're just looking at diagonal truth. So if one's true and the other's false. So it'll give you the singleton containing the true answer here, if there is one true answer. And then I'll say it just spits out the whole set otherwise. So I can write the truth conditions for Boolean disjunction with the help of this answer operator. Just ignoring the y parameter for a second, right? Or actually, no, don't ignore it. I'll say MYX now in 2 dimensions satisfies phi or psi, just in case there is a member of the answer set, if you want, but relative to y, the world is actual. Call that member alpha. This is quantification over sentences where alpha is true at MYX. Right. So this is sort of going to, even inside modal operators, this is going to look for what's the actually true answer, even if we shifted away from the actual world under the modal operator, what's the actually true answer to the disjunctive question P or Q? So that's a fancy way of writing a 2-dimensional disjunction, kind of like the whether in 6, the whether P or Q in 6. But that can be written in the language of 2D, so the basic language. So, you know, phi or psi can be written as, well, if it's actually the case, this is a, you know, three-part conjunction. If it's actually the case that phi and not psi, then phi, because that's the true answer to, at the actual world to the question phi or psi. If, on the other hand, psi is true and phi is false, then psi. But if if they're either both true or both false, then take the Boolean join. In other words, you'll get both of these, and then you're going to quantify existentially over it. So that or can, you know, isn't a primitive in the language because it can be written like this. And that disjunction, it's idempotent, commutative, associative, and it does generally classically validate or elimination, for what it's worth. From phi or psi and not phi, you can conclude psi. Of course, it's not the Boolean join, but it shares these features with the Boolean or. So just to summarize where we are, I sketched some theoretical roles played by operators, especially dagger, in natural language communication, right? So the dagger's interesting in sort of the way that Stalnaker shoots it, for example, because it's not anchored to the behavior of any natural language operator or adverb, right? Actually is a word in the English language. Whether it behaves like this operator is a contested question. But the dagger, there's no one has ever conjectured that there's a word in English or indeed in any natural language which is or approximates the dagger. Nonetheless, if Stalnaker's right, daggerization, diagonalization is ubiquitous in communication and rational thought. But it has no, in natural language, it's not lexicalized. And then, of course, we sort of work with the assumption that the modals are lexicalized in natural language. So we motivated this activist framework, and then we sketched this two-dimensional, what Lloyd calls an isotope of a disjunction, right? A generalization of disjunction to 2 dimensions, which goes Boolean for what it's worth on the diagonal, right? That's why I'll get the lobbies for the middle and other such tautologies in the propositional fragment of the language. So now we sort of, we're still not even at the point where we have deontic operators, right? All I have is the box. But what I'm going to do is I'm going to treat deontic accessibility as a sub-relation of the S5 box relation. So it's also going to be confined to the horizontal, and it's going to do its usual job. It's going to take you from a world to worlds that world sees as ideal in some deontic sense. But I've now sort of laid a framework where I can block this inference, right? From op P, you can conclude op P or Q for the same reason that it's going to be invalid to go from box P to box P or Q. Okay, so, but it will be a priori, right, that or introduction is valid. So from you post the letter, you can conclude that you post the letter or burn it. This is a priori consequence. And again, we can just write that as, oh, sorry, this should be the other form of consequence. AP entails A, P, or Q. And that, decomposing the A, is just box dagger P entails box dagger P, or Q. Okay, so there's an intermediate goal. I have about 5 minutes left, right?
Yeah.
Okay. Yeah, I'll just stop when I get.
Actually, it's about 10 because we started about 5 after.
Okay. So I'll just see how far I get. Where are our deontic operators? Right, we didn't put them in anywhere. You know, let's take a look at the Fritz homomorphism again. These boxes were the S5 cells that you get from just your, oh, sorry, that should be a white box. But, you know, these are the little cells that you get for epistemic, for metaphysical possibility, and they're sort of approximated by rows of the matrix. And so what we want to do is just take these rows and then add non-trivial R relations. Not this one, this one with the black arrows, because that's actuality, that's the actually operator. but it could look like that. So now we get to what deontic logic is like, at least in the literature, the standard literature, which treats the deontic puzzles like Ross's puzzle, and free choice permission. So here's, I think, some reasonable principles, which are sort of typical in that literature. One is that may implies can. So our deontic relation, if we're going to add it, should be a subrelation of metaphysical possibility. Another is seriality, right? So this is taken to sort of be an a priori truth about deontic logic. Diamond top is always true in deontic logic. The nice thing about moral obligation or whatever we're modeling with that relation is that there are no dead ends. No matter how crappy your deontic choices are, there's always something that's least bad, right? So that's actually one of the only axioms you get in standard deontic logic is diamond top. So ought entails may. This is may entails can. And then there's this other property that I like called shift reflexivity, which people have discussed in the literature, but not all that much. And that's to say that, well, I mean, it's written here. If X sees Y, if X sees V as ideal, then V sees itself as ideal. Because you can't start out of the actual world, sort of do what you ought to do, or sort of go where you did according to W what you ought to do, and then sort of be sent back somewhere else. So things that are ideal are self-affirming in some sense. So if you're going to write those out with a typical language, so let's just introduce O for ought, right? And it's anchored to this new relation that we'll add on our layers. And may implies can, so O hat, the may, entails diamond, OP entails O hat P. And then here's how you write shift reflexivity. It ought to be the case that if it ought to be the case that P and P. So that'll be our sort of deontic trio. So what we want to do sort of now is, there's sort of two ways of looking at what we're doing. We're starting with, say, these worlds, right, that just make the distinctions between P or Q, but now we've stretched this out into a two-dimensional array. And let's say that these are the deontic accessibility relations, right? So you can ask yourself things like, well, how is deontic accessibility supposed to work if you're visualizing it in a matrix? For example, could what a world sees as deontically ideal depend on which world is actual? Like, what would that mean? We already have a notion in our simple models, before we go to matrix models, that what counts as ideal can depend on the facts on the ground. Whether I owe you restitution depends on whether I committed a crime against you or something like that, perhaps. But now there's this extra dimension of variability that doesn't get a lot of intuitive traction, I think. So what I'm trying to motivate here is I'm trying to motivate what, again, class of models that we're interested in before I start exploring what the relative completeness results would look like. So consider, a principle of deontic rigidity. So deontic rigidity says that if something's permissible, then it's metaphysically necessary that it's permissible. So this would be something like, this would enable something like what you get in standard deontic logic quite a bit, the Anderson-Kangar reduction. So ought phi can be paraphrasable as, call this atom D. D says something like, all requirements are met. So when I say ought phi, what I'm saying is that metaphysically, D entails phi. You sort of have to do phi to wind up in the D space, the space where everything's good, sort of from every point of view. O hat phi, so it's permissible that phi will say that, it's metaphysically possible that everything is good and phi is true, along with phi. Phi is consistent with everything being good. So this, again, just says if W is R related to V on the row, right, and W sees a world U as ideal, then V also sees that world as ideal. So this is sort of not, this is going to D, right, in this model, where all requirements are met, is itself going to be acvist, right? It's just going to be the proposition that's like true here and true here and false here and false here. Another principle worth considering right? Do we want something that we can call Deontic Uniformity? So R is going to be uniform just in case, if you have X, Y, v, W, and V, then if these two ordered, if X, W, and X, V are related via the Deontic accessibility relation, then Y, W, and Y, V are related, right? So this is to say, sorry, this was the principle I meant to describe earlier, which is if you travel up and down here, you're not going to get a variety on what counts as deontically ideal. So that seems like, again, a principle that seems seems attractive, but I think is controversial. It's interesting to try and imagine what counterexamples you could have to these sorts of properties. You can, of course, axiomatize this also. In 2 dimensions, what we're asking is whether this property U obtains. So that's to say, aught phi is equivalent to dagger aught phi, where phi is explicitly a 1D formula. So that's going to be actually n dagger phi. So those are more choice points, and then I have some further completeness results for those. What I did want to say eventually that I'm going to be getting to, and I'm not even sure this is in the slides, but it is on your handout, is what I want to get, right, with appropriate restrictions on the Deontic accessibility relation is to prove one, right, is to prove that if you may have an apple or a pear with our or that's non-Boolean, then you may have an apple and you may have a pear. And I do have to add 2 extra premises to get that, which are listed on the last page of your handout, but I'll go ahead and stop here.